Alright, welcome to my video on gravitational force and how we get the acceleration due to gravity. And the acceleration due to gravity gets its own script, little g. So anytime we're saying the acceleration due to gravity, little g is going to get represented by that. So when we talk about the gravitational force, and let's talk about fundamental. Fundamental. That might be an A. So the fundamental gravitational force. You don't need to worry about this right now. In week 10, we'll talk about this in a lot more detail, but it's the force of gravity is equal to big G, which is a fundamental constant. It's called the gravitational constant. The mass of one object, the mass of a second object, divided by the distance between the objects squared. So when we're thinking about this, if we're talking about, I guess I'll draw the Earth as blue. So if we're talking about the Earth and a person standing on the Earth, then the force due to gravity is going to be G times the mass of the Earth divided by the radius of the Earth squared. I'm going to kind of put that all in brackets, times the mass of the person. And I say the radius of the Earth because we talk about the person standing at the surface of the Earth, and I probably should draw on the person smaller or the Earth bigger, but it's the fact that the distance that we use in this is from the center of mass to center of mass. So it would be from the center of the Earth to the center of the person, which we can pretty much just say approximate as the radius of the Earth. When we put all this stuff together, and I've bracketed it off, all of this combined gives us G equals, and we're gonna 9.8 meters per second squared. And we'll go through, I'll make you calculate, and then we'll do this a bit more. But what this lets us say is the force of gravity, and I've switched to little g here because now we're going to be talking about the force, little gravity, is the mass of your object times g. So this is the force due to gravity at the Earth's surface. Now, if we were on the moon, we could end up saying, well, the mass of the moon divided by the radius of the moon squared, and then we could say, oh, we have a different acceleration due to gravity at the moon's surface, or at Mars's surface, or other planets. And we'll talk about that in a lot more detail, as I said, sort of in week 10. But if this is the only, so now that we have this force going on, well, we have this force, so if this is the only force, then the net force is equal to F sub g. And Newton's second law F net equals Fg equals mg. So sorry, doing too many equals together. Let me be a little bit more careful. So F net equals ma, which is Newton's second law. But then when I plug in this equation, combined with the fact that the only force is the gravitational force, so we would have the net force, which is equal to Fg, which is equal to the mass times the acceleration due to gravity. So that lets us say the mass times the acceleration due to gravity is equal to the mass times the acceleration. So the acceleration due to gravity is the acceleration of the object if this is the only force acting on it. And that's where this all comes from. All right, so that's where the acceleration due to gravity comes from. That's where its name comes from, and it's equal to 9.8 meters per second squared. And the thing that I want to say is if you have g, it's positive 9.8 meters per second squared. If you have negative g, that's where you can then give it the negative 9.8 meters per second. But g is always defined as this, with the positive there. It's only once you start talking about your vector and therefore your direction when you should be assigning a sign to g. And I will do an example to clarify my point. So I have this example problem. So at time equals 0, I'm going to drop a ball and it's 1.5 meters from the surface of the Earth. So in this case, this is what we call free fall. So the only force acting on it is gravity. It's one of those things where I could draw my free body diagram, and I'd say, oh, well, it's not in contact with anything. We're going to assume it's at the surface of the Earth, so the only force acting on it is gravity. So again, F net equals ma from Newton's second law. So with that combined, that lets us then say that mg equals ma. So g equals our acceleration. Now this is where I needed to have been a bit more careful. And when I'm talking about these, I should have decided on a coordinate system. So I need to say up is the positive direction. So when I say I have the force of gravity is going down, well, that means my net force is actually negative the mass times gravity. So my acceleration is actually negative g. So again, g is just 9.8 meters per second squared. So all this together lets me now say my acceleration is equal to negative 9.8 meters per second squared. Which, for simplicity's sake, I'm just going to keep saying is negative g until I have to get my final answer. Because writing little g is a lot easier than writing 9.8 meters per second squared every time. So in this case, I now have a constant acceleration. So the problem is one-dimensional. I don't want to keep using red. The problem is one-dimensional. And we have constant acceleration. And so one-dimensional, comma, constant acceleration. So this lets us use the kinematic equations we had talked about previously. X equals x naught plus v naught t plus 1/2 a t squared. Now that I've gotten this far, I realize I forgot to ask the question, or how long to hit the ground? That's the question I'm being asked. So in this case, I'm going to say this 1.5 meters, I'm going to call it height. The other thing that I need to do in this problem is then I need to decide where my variables are equal to 0. I'm just using x as position. It's probably going to drive you crazy that you're saying, why aren't you using y instead? And the answer sort of comes down to it's all variables. As long as I'm not using x and y, this is fine. I can totally say that up is my positive x direction, and it's not the standard way of saying it, but it's the bed I've made, so I'm going with it. So looking at here, and when I have this equation, I have to think about, well, what of these do I know? Well, I know the final position is when it hits the ground. So my final is 0. It starts, its initial position at time 0 is the height. So what's the initial velocity? Well, that's where, looking at this, it says it's dropped. So that dropped actually tells us the initial velocity is 0. And then we have to think, well, what's our acceleration? Well, it's in free fall. I kind of used, I've used forces and Newton's second law to know that the acceleration is going to be negative g. So all this combined together lets me say 0 is equal to h minus 1/2 gt squared. So I can pull this over to the other side of the equation, say 1/2 gt squared equals the height. Then multiply both sides by 2 and divide by g. So that when I do that, the 2 cancels the half, the g cancels the g. But I have to remember I'm doing that to the other side as well. So t squared equals 2h divided by g. So the time is going to be equal to the square root of 2 times the height divided by the acceleration due to gravity. So going through solving this with symbols, 1, I didn't have to keep writing 1.98 meters per second squared in every single one of these steps. 2, I didn't have to write 1.5 meters in every single one of these steps. And 3, I've now created a general equation that works for any height and on any planet. So solving everything symbolically gives you more power in the end. It also makes it so that I don't accidentally mistranscribe one of these numbers somewhere through there and everything goes bonkers. So now that I actually want to solve this problem, that's where I can say the time is going to be equal to the square root of 2 times 1.5 meters divided by 9.8 meters per second squared. So I'm going to just overdo this just a little bit. So that's 3. I have meters in the numerator, meters in the denominator. So those meters cancel each other. I have seconds squared in the denominator of the denominator, which actually moves it up to the numerator. So I have 3 seconds squared divided by 9.8. I will snag my calculator, and I will say the square root of 3 divided by 9.8. So the time that I'm getting is 0.55 square root of seconds squared, which, thankfully, the time we're getting is 0.55. The squared and the square roots cancel out. So 0.55. And I'm just going to write out seconds because my S's and 5's look way too similar. So, hope that helps you see where the acceleration due to gravity comes from, and sort of another example of how to do a 1D constant acceleration problem, specifically with gravity as being your only force because you're in free fall. Thank you for watching.